Okay, so we'll get started here. Just a recap, we were talking about naming and distributed naming systems last time. Uh, the important thing to keep in mind is most objects, resources, machines in distributed systems have names that users give them and refer to those objects, machines, resources by their name. And the system has to map it to the underlying resource, which is the job of the naming system. And the main takeaway was when you have very large distributed systems with lots of objects, the naming system itself has to be distributed to scale to this very large system. And we looked at the example of DNS, which is the naming system for an internet, clearly one of the largest distributed systems out there as a whole. So we saw how you can have a distributed naming system that's hierarchical. I talked about LDAP, Lightweight Directory Access Protocol, which is an alternative naming system used more in LAN environments within organization. Also hierarchical, little more general. Okay, so those are two use cases of how to build naming systems with hierarchical namespaces. And that's all we are going to discuss as far as naming is concerned. That was an entire chapter which we really discussed in one lecture. Okay, so but we'll now move on to the next topic, which is going to be on canonical problems. So this is sort of the middle third of the course where you learn about some fundamental problems that arise over and over again in distributed systems. So in some sense, these problems we will discuss in the abstract, but they're really critical. They arise over and over again in any kind of distributed application. You may have already encountered synchronization or mutual exclusion in the first lab. You have to deal with that. But there are many other problems like that: leader election, deadlock detection, clock synchronization, all of which are very key, okay, to the design of distributed systems and applications. So we will look at them. We will, rather than looking at a distributed application and trying to see how these problems are solved in that application, we'll just abstract it out. We will not worry about which problem you're trying to apply to. Just look at the problem itself, which is clock synchronization or mutual exclusion, and see how to do or how to address those problems in a distributed context. Okay? So we are going to spend the next several lectures talking about a variety of these, and I've added some new ones here, such as consensus and faxos and things like that. Okay? So we'll talk about all of them. Okay? Today we'll start with clocks, clock synchronization, and logical clocks. Okay? That's the first of the many problems. So we'll try to understand what is this problem, why is it important, how can you go about addressing it, and so on. So first thing to keep in mind is every machine that you have has a built-in clock. Okay, computers are clock, phones are clock. So usually the clock is a chip called a real-time clock chip that is running on the machine. The clock keeps ticking. Okay, usually the machine may have a battery, so the clock will keep ticking even if the machine is turned off, and it allows the machine to tell what time it is. Okay, this is how your machine knows what time it is. That it's 5:05. As a clock chip that's going to tell you what is the current time. Okay. Now, in a distributed system, you have independent nodes that communicate over a network. So we'll assume each node has its own clock. Each node is a machine, so it has its own clock that is going to tell the machine what time it is. Okay. Typically, these clocks are chips that use crystal-based clocks, so they look at the property of the crystal. Okay. Typically, it's a material property. So if you use a quartz crystal, such as in quartz watches, this quartz crystal will oscillate at a certain frequency. Okay, so depending on how many times it oscillates every second, you will count that and you will tick the clock by 1 second when it's oscillated by that many. This is how crystal clocks work. It's not important to understand crystal clocks itself, but just keep in mind that there are chips that will tell you what time it is. And now, as far as distributed systems are concerned, or even applications are concerned, you have to ask, what do we use this timing for? Clearly, you may use it to tell what time it is, but as far as applications are concerned, what they may do is they may timestamp certain events. Okay? They may look at the timestamp on a certain object or an event and try to reason about what that timestamp is telling you. Okay? Simplest example is if you try to compile a large application that consists many source files. you often use programs like make to run a build process. What make does is it does what is referred as incremental compilation. If you have 100 source files, and let's say you compiled all of those 100 files and created a binary for your application, and then you go and change only one file, you make some modifications to the source code and you want to recompile. Okay. What make will do is, rather than recompiling all of them again, it will only see which files have changed and only compile those. Okay. This will save you some effort, saying why compile files, C file that may not have changed. Okay. It's unnecessary work. You can use the results of the object code that is generated from the previous compilation once again, rather than recompiling it. Okay, and the way this is going to work is you are going to, you have to ask, how does make know what files have changed and what files have not changed? Okay. It basically tries to reason about it by looking at the time of creation of the object file and the time of modification of the source file. Okay. If the source file is newer than the object file, it means the source file was changed since you compiled the file previously. Because it has a later timestamp. Okay, so you will recompile. So simply by checking the file modification times on the object file and the source file, you see which is newer, which has a later timestamp, and then you recompile. Okay. This is how make works. Okay. Now, if all of this was happening on a centralized system, there wouldn't be a problem. You change some files, you recompile, new binaries created. Okay, but what often happens in software development environments is the build machines which actually compile may be separate from the development machine. You may have a workstation where you have an editor and you are making changes and you save and then you say go build, and then you have a set of build servers that are faster machines that can run very fast compilation jobs. For very large projects, it may sometimes take hours to build the entire project, so you have faster machines to do that, not your own workstation. So you have two sets of machines, a machine that runs the compilation and a machine where you do your local edits. Now, if you want to use make in this environment where there are two machines, you can have bad things happen if the clocks on the two machines are not synchronized. Yeah, because each machine has its own clock, that's what we said. So in particular, what may happen is you may compile a file, okay, on the build machine, and the build file gets created. It has a timestamp that machine has given it. That's the time at which it was created. Then you go and say, I made some small mistake. I go open up a source file, you make some small change and you save it. Right? And you say rebuild. And now when you save it, your source file also gets a timestamp. Okay. Now ideally, if the clocks were synchronized, the timestamp on the source file will be later than the object file because that event happened later. You compiled, then you edit it. So the source file will have a newer timestamp. But what if the clock on your workstation where you compiled is slow? It runs behind the clock on the build machine. Let's say your clock is 15 minutes off. It's 15 minutes behind the build machine. So although in reality you actually edited the file after you compiled, the timestamp that your machine is going to assign it is whatever the local clock says is the time, and the local clock is 15 minutes behind. So it will get an older timestamp. Even though you may have modified it now, you may get a timestamp 15 minutes before the actual time it was modified. Now, if the build machine tries to rebuild this, it will actually see an older timestamp than the build timestamp. Because you did a build 1 minute ago, then you modified, but the modified file is an old timestamp 15 minutes back. So if you simply compare the timestamps on the file, make will think nothing has changed, won't recompile. Okay. Your build process will run, and then you will look at your binary and see something is wrong. I made this change, but it's not showing up in the build that you just did, and you will feel that something has gone wrong. Now this simply arises because the clocks are not synchronized. Some clocks run faster. As you know, real clocks can run faster or slower than real time. The same is true of computer clocks, is it? Okay. So this should tell you that unless you have synchronized clocks, simply looking at timestamps that are assigned to objects or events on two different machines and comparing them is a futile exercise. The clock values are meaningless if the clocks are not synchronized. Is that clear? Anything I can answer here before I move on? How to do clock synchronization? It should be clear why you need clock synchronization. So if you want to look at timestamp and reason about what happened first, whether the object code was generated first or source code was generated first, and you need to recompile, that's what you're trying to reason in the case of make. You need to understand the order of events. And here you are trying to understand the order of events by simply comparing the time stamps assigned to files, modification types. Okay, so that should tell us why we need synchronization. So now we'll talk about how to do synchronization. We start with physical clocks. Okay, so you should know how you tell time. Okay, basically you say time is noon when the sun is directly above your head. That's roughly how people used to tell time in the old days. You used to have these poles that cast shadows, and you look at the shadows and say what time it is. When the shadow disappears, the sun is overhead and it's noon, essentially. Okay? So that's how you used to tell time in the old days. Now you don't use that mechanism. You have much more accurate clocks called atomic clocks. Okay? So these are very accurate. So they basically lose their accuracy is 1 part in 10 to the power 13, which means that they will lose a second or so of time every million years. Okay? So they're the most accurate clocks that you have today. So now you say it's noon, and your atomic clocks tells you when it's noon, not when the sun is directly overhead, because this is even more accurate than how the earth rotates in terms of accuracy. So you tell time today using atomic clocks, not using the sun, okay, which is astronomical time. And all other clocks that you have are going to be less accurate than atomic clocks. Whether it's your wristwatch, whether it's your clock on your phone, clock on the computer, they will all be less accurate than an atomic clock. So they will drift. Okay? So basically what drift means is they will actually be off with respect to real time. Okay? Now, we only know real time based on atomic clock, because that's our reference. Okay? That's the most accurate clock we have. So all other clocks are less accurate. So somehow we have to synchronize it with an atomic clock whenever it drifts from real time. That's really the gist of what clock synchronization actually tells you. Okay? And there are there are time zones and so on, that basically every time zone has its own notion of how off it is with respect to another time zone. So typically, the way you had time zones, or there was this place in Greenwich in the United Kingdom, so you had something called GMT, Greenwich Mean Time, and all time zones were either half hour or an hour apart from GMT. Now that is referred to as UTC, Universal Time. So you don't actually refer it by location. So that is basically where you will say it's noon, and every other place has to say, how many hours apart are you from that place? So that's how you'll figure out what's the local time at any particular place. Okay. And the way each time zone actually keeps time is that you have atomic clocks. So in the US, you have a set of atomic clocks that are based in Boulder, Colorado, that will tell you what the time is, and they broadcast this time. Okay, so any receiver that can listen to this broadcast can figure out what time it is based on this atomic clock. So many countries have their own atomic clocks, and they broadcast this time. So it doesn't matter which atomic clock, you have to synchronize with some atomic clock and then figure out what the time is. And these are very accurate. Okay? There are also satellites that take the time from an atomic clock and broadcast it, as you will see. Okay? So the basic idea behind clock synchronization is, given any physical clock, whether it's a wristwatch, whether it's a computer clock, you have to basically use some authority, which is the master clock, and synchronize. Whenever you are off, and if that clock says it's, let's say, 10 o'clock, then you change your time to basically match whatever that time is. That's really the basic idea behind clock synchronization. Okay. Any questions here on physical clocks? Yes. Okay. Question is, how often do you do clock synchronization? As we will see on the next slide, to an extent, it will depend on how accurate your clock is or how inaccurate it is. Okay. So you will see that you can specify an error tolerance on how much you are willing to let your clock drift from real time, and that will tell you how frequently you have to synchronize it. Okay. Okay. So that's the question we are going to answer in the very next slide. Are there any other questions on clock synchronization? Okay. So here is basically a slide that answers that very question, saying how often do you want to synchronize. Okay. So we will basically answer this in a slightly more general way. We'll look at this picture here. This picture is a graph that has two axes. The x-axis is UTC. Let's say this is real time. Okay. And the y-axis is whatever time your clock tells you it is. Okay. So basic idea is, if your clock is perfect, if it's a perfect clock, every time real time advances by 1 second, your clock should also advance by 1 second. So then both are in synchrony. Okay. So your clock always tells you what the real time is. Okay. Now most clocks, as I said, won't be that accurate. They will either run faster and slower. So this dark line here is the perfect clock. This has a slope of 1, which means every time this clock advances by 1 unit, this clock will also advance by 1. Perfect clock with slope of 1. Real clocks will be either faster or slower, as you'll see. So this dotted line here is a slow clock where every time this real time advances by 1 second, this clock advances by slightly less than 1 second. So over time, this clock runs slower. So it will start drifting. Okay, so this is dotted line is going to tell you when it's time t here, what does your clock say? It's going to be less than time t. Okay? And this other line shows a fast clock where whenever time advances by 1 second, your clock advances by slightly more than 1 second, so it runs faster. Okay? So the slope of a slow clock is always going to be less than 1. The slope of a faster clock is greater than 1. So it is a greater slope than a perfect clock. Okay? So either of these two will have a drift. Okay? Drift is the amount by which you are off with respect to the perfect clock. Okay? So let's say your clock, whatever it is, has a maximum drift rate of rho. Okay? That's the maximum amount by which your clock will drift. Right? Most clocks will drift by different amounts depending on other conditions such as environmental conditions. So if you have a quartz watch, for instance, it runs using this notion of how frequently does a quartz crystal oscillate. That frequency actually is determined also by temperature. Okay? So on hotter days it may be slightly off, and on colder days it may run slightly slower. So it is not going to have a exact drift rate. So the drift rate itself may change. But let's say the maximum rate is rho. Okay? So this is like saying this clock, regardless of what temperature conditions or what the environmental conditions are, will lose no more than 1 second every day. That's the amount by which it will drift. So you can pick whatever value it is for whatever clock you're trying to figure out. Okay? So if it drifts by maximum of rho, what that means is it will be either between these two values, 1 minus rho and 1 plus rho. For every time clock ticks by 1 second, you will either tick by 1 plus rho or 1 minus rho seconds. Okay, because that's the drift rate. Okay. So what that also says is if any two clocks will drift by at most 2 rho times delta t in time within any time delta t. So the worst case is if you have two clocks, one is a slow clock, one is a fast clock, both have a drift rate of rho, then they will be off by at most 2 rho because one clock is slower, one clock is faster. That's the amount by which you can bound any two clocks with a drift rate of rho. Okay. Now, to answer the question, how frequently should you synchronize? If you want to limit the amount of drift to delta, it says I don't want this clock to be off by more than delta seconds, and you can pick whatever value of delta you want. Okay. So then you say how long does it take for this clock to go off by delta, which is basically going to be given by this value. Okay. So then you would say run your clock synchronization every delta over 2 rho. So it basically says, let's say this clock drifts by 1 second for every 24 hours. And you say, I want this clock to be no worse than 5 seconds off. That means you should synchronize every 5 days. Because over 5 days it may drift by at most 5. Every day drifting by a second. So you see how long it takes to drift 5 seconds. So you say so I need to synchronize once every 5 days. So you can pick these values and basically that's what it's saying here. Delta over 2 rho. That's the period with which you should synchronize. Okay. Now, how to synchronize, we have not said. All this says is how frequently to synchronize. Okay. Is that clear? Any questions on this? Yes.
If you know the rate of drift, why can't you use that to synchronize the clock?
Okay. Question is, if you know the drift rate, why can you not use that drift rate to synchronize the clock? So if your drift rate was constant, if you knew that every day it would lose a second, then every day you can reset your clock by a second. Okay? But that assumes that the drift rate is constant. As I just said, the drift rate will vary. It will depend on the temperature and other conditions where the rate at which a crystal oscillates may depend on how hot or cold it is. So you will not actually know the drift rate. You can only bound the drift rate. Okay? This is the worst case. What has actually happened, you don't know. If it's a constant rate, then you don't need anything. You know it is going to lose a second, and you know it's always going to lose a second, then you reset by that amount. But here, that's the worst case. It may drift up to a second. It may be less. So then you don't know how you can adjust it. You need some other authority to tell you.
How do you determine the maximum
Okay, question is how do you determine the maximum bound on the different that could either be measured based on subjecting the clock to different environmental conditions. You could get it from the property of whatever material you use for the clock. Okay, so I think it has to be determined from other means, either to actual measurements or some such thing. Okay, but we assume that that's known. Okay, we will not see how to determine rho. Okay, so first algorithm. So we'll start very simple. Okay, so these algorithms may sound almost trivial, but they are actually at the heart of how clock synchronization works. So first algorithm is called Cristian's algorithm. So what now we know how frequently to synchronize. The question is how do you synchronize? Okay, the answer is very simple. We'll assume that there's a machine called a time server. That time server is going to tell you what time it is. Okay? And all other machines will synchronize with that time server. Okay? Now you have to first synchronize the time server itself, because the time server itself is a computer. Okay? So we'll assume the time server has some ability to synchronize with an atomic clock. Okay? You can buy one of these dongles, a USB dongle that you can connect to a machine. The USB dongle is an FM receiver that actually receives broadcasts from atomic clocks. Okay? They're not very expensive. So you can simply connect that to a machine and then read whatever the receiver receives, and you can reset your local clock to that atomic clock frequently. So then your machine will be perfectly synchronized, well, not perfect, but reasonably well synchronized with an atomic clock. So there are many ways by which a time server can be synchronized with an atomic clock, but let's assume that you use any such technique. So now for your network or your system, that is the authority. That's the machine that knows what time it is. All other machines have to synchronize with that atomic clock, or rather with the time server, which is itself synchronized with atomic clock. So the way this works is machine P, every delta over 2 row seconds, because that's the frequency with which we are going to run the synchronized algorithm. So every delta over 2 row seconds, a machine is going to ask the time server, what's the time? Okay? Time server is going to say the time is whatever it is, 10 o'clock or 9:30 or some such thing. And then you simply have to take the value that the time server sent you and reset your clock to that time, and you will be synchronized. Okay, that's the basic algorithm. Now, having said that, you have to realize that you have to correct for network packet delays and so on, and that's what this figure shows. So let's say at time t shown here, so the vertical axis is time here. Okay? This is machine P, that's the time server. This is what is happening on machine P, that's the time server. So at time t, not time t, at some time here, t prime, this machine is going to start the clock synchronization algorithm, send a message to the time server saying what time is it. Okay? That message will be received at this point in time, the arrow hits this one. Okay, and then that message will be processed. Okay, by the time server, it will read its own clock, okay, and then send back a reply saying this is the time. Okay. Now, if you simply set your clock to the time that was sent to you, you will see that there is going to be an error already, because the network packets don't arrive instantaneously. They take some time to arrive over the network. So at the very least, you have to actually correct for this time. Essentially, if you knew how much time it took for the packet to arrive, you should set your time to t plus this delay here, which tells you how long did the packet take to arrive. Okay, so you should actually set your time to t plus t reply, which is the time the packet took to arrive. Okay, yes. You're saying you should also account for how much time it took you to process the message? Yes, so you're right in that this is simplified in that once you receive the packet, you have to process the packet and set the time. That will also take some delay. You're absolutely right. So I'm ignoring that for a moment. I'm simply trying to show how to account for processing delays. There are other delays you'll have to account for as well, because you'll see that this packet here took some time to process as well. It was not instantaneous. So packets don't arrive instantaneously. Messages cannot be processed instantaneously. So really all algorithms are going to differ in how they are going to estimate the processing delay and the network propagation delays. Okay? The basic idea is very simple. You ask the time server what time is it, it tells you the time and you set it. Okay, but you have to realize in reality it's going to take some time for your message to reach, for the message to be processed and to get back a reply. So how do you estimate all of those other times and actually add it to the time value you received from the server and set the time? That is basically where all algorithms are going to differ. The better estimates you have of those values, the better your clock synchronization will be. The worse estimates you have, the worse it will be. The most naive algorithm doesn't do anything to correct. It simply sets the time to T. So you know you're going to be off in any case. Yes, question. Okay, so you are saying let's send this time here to the time server, and it's going to say you are off by delta. But then when you receive, you still have to account for the time it took for your packet to reach them. So you will send, if you send a packet at time t prime here, right? So the only way is if that message went instantaneously, then you would know what the actual drift is. But that propagation delay still has to be accounted for. Okay. So this is basically at the heart of how clock synchronization algorithms will differ from one another. How will they estimate this value? Okay. Here we are going to ignore processing delays, okay, just for simplicity. We'll just try to account for network propagation. So you will say, how do I estimate this time? Okay. So simplest way you are going to estimate this time, and this is just approximation clearly, is you will see what time did you send the message, that you know. Okay. You will see what time did you get the reply, that also you know. That's basically the local clock. So you will take the difference between these two times and you will basically say, let's assume the forward path and the backward path took the same amount of time. So I'm going to just take that estimate and divide it by 2 and assume that this value is actually half of that value. You'll see that that's not true even in the picture. You see that it took longer for the message to go than to be received, because that depends on the network condition. If the network is a little more congested, it may take more time for the packet to go in the forward path than in the backward path. But this is a reasonable first estimate that you can make. Say I sent the value at time t, I got the reply at time t prime. You take the difference between the two, you half it, and you say that's the time it takes for the message to come back. So you will take whatever time came from the clock server, you will take this value, you will add it to that clock and set your clock to that value. Now you can make multiple such measurements, so you get an average. So if you have off in any one value, you take the average value and you can improve that estimate using any number of means. But this algorithm is going to just make one measure. There are others that will make multiple measurements to get more accuracy. Yes, question. Okay, what if the question is, what if the network packets get lost? So then you don't do anything. You will not get a reply. There's nothing to do. You just restart the process in this case. Okay, so you just, if you don't get a reply, there is no, you can't even set your clock. So you just say, I didn't get any reply, restart the whole process. So eventually it will succeed and you just use that value.
So you have like a default timeout.
Yeah, you can always use a timeout to send that packet and get a reply and so on. So, assuming you use UDP. If you're using TCP, TCP will retransmit. But then you will be even more off than the estimates, because this is not assuming there are multiple retransmissions. Okay, so this is Cristian's algorithm, very simple. Okay, so you are going to, basic point is you have to somehow estimate the network propagation. Realize that we ignored the processing delay, which you also should have estimated. Okay, but we ignored that. Okay, that also you can measure, saying at the server, typically when you receive a message, how long does it take you to process, and you can get those measurements and add it, but we have ignored those. Okay. So this is using a time server. It's a centralized algorithm. Keep that in mind. Just the time server is a central entity. Time server goes down, clock synchronization won't work. Okay. Single point of failure. Never a good thing in a distributed system. Okay. Second algorithm is going to be another algorithm called the Berkeley algorithm, designed by some people in Berkeley, so it got its name. It was used in BSD, which was Berkeley's Unix distribution as well. So what this does, this algorithm does, is it doesn't synchronize all the clocks on machines with respect to an authoritative time server. Okay? It just synchronizes them with respect to one another. Okay? So all clocks, let's say, on machines in the Ed lab will all be synchronized. Okay? But they will not themselves be synchronized with some external entity that tells them what the real time is. So that's the basic idea. So and the reason for this is, if you are simply trying to compare timestamps that these machines all assign to some events, those clocks have to be synchronized with respect to one another at the very least. Okay? Whether they're synchronized with the external world is not that important, at least for reasoning about events that these clocks are being used to assign to events. So this is relative clock synchronization, not absolute. Machines in a network are synchronized with respect to one another. What the real time is may be completely different from what time these machines think it is, but their clocks are synchronized. And that is what might matter for events that are happening within that system. Okay. So here is how this works. So again, we'll start with the centralized version of the Berkeley algorithm and then talk about a decentralized version. So you do have a time server, okay? And then there are other machines. In this case, the time server is not synchronized with any atomic clock. It's simply a server that's going to run the algorithm. Okay? So every so often, okay, these machines will basically run a clock synchronization algorithm, and they will simply say, I think here is my time. Tell me what time I should reset my clock to. Okay, so here you see that the time server thinks it's 3 o'clock. Okay. This machine thinks it's 2:50, and that machine thinks it's 3:25. So this is slow clock off by 10 minutes. That's a faster clock. That's 25 minutes. So each of them will broadcast their values. So your algorithm runs by the time server itself, starting the algorithm and saying it's 3 o'clock. Tell me what time you think it is. So it's sending this packet saying it's 3 o'clock to all of these. So now each machine is going to send their local values. In this case, we are simply sending the delta. This machine says it's 250, which says it thinks it's minus 10 from your clock. This says it's 325, which says it's plus 25. And then what the time server is going to do is it's going to take all the clocks, take the average, okay, and send back that value. Okay, so the average of 250 and 325 happens to be 305. So it's going to say this is the average value in the system. I don't know who is right, who is wrong, who is fast, who is slow. So if you say think approximately some clocks are faster and some are slower, let's all tick at the average rate of the average clock in the system, and that may be the right thing to do. So you simply set the value to 305. You compute the average and you broadcast that value, and then everyone sets their value to 305. Okay. And even in this case, you have to account for propagation delays and so on, which I have ignored here. Okay, I'm just explaining the higher level concept, so you'll assume that you will still do whatever you did in Cristian's algorithm to account for message delays. Okay. So the basic idea is you ask everyone for their time, you compute the average time in the system, set everyone to the average time. So all clocks tick at the average rate. Okay. So if some clocks are faster and some are slower, then you will basically correct everyone. If you have a system where everyone is faster, then this is not going to actually correlate with anything real, but clocks themselves will be synchronized with respect to one another. Okay. So you can simply use a distributed version of this where rather than using a time server, you basically just ask everyone to broadcast their time to everyone else, and you can just compute the averages locally. If everyone told you what their clock value is, you can just take those values and compute the average. Okay, so that's basically a decentralized approach. You can also try to ensure that there's more accuracy by throwing out very high clock values or very low clock values if the clocks are faulty. Not just they're drifting, but they're actually faulty. Okay, because sometimes clocks may just develop fault. So you can throw the outliers out when you compute the average to get a better estimate. So those are all improvements that you can make today. So with respect to what is done today, you can use a protocol called NTP, Network Time Protocol, that uses similar concepts. NTP assumes the presence of network time servers, where the time servers can be synchronized with another time server or with an atomic clock. And then your machine has to find some time server that speaks NTP and synchronize with it. So then we'll see how to do that as well in a slightly later slide. But it basically uses a version of Cristian's algorithm in some hierarchical fashion. Okay. There is a utility called RDate, which is not a clock synchronization utility. It is simply a utility that you can query another machine for its clock value and if necessary reset your clock to whatever comes back. Okay, so early versions simply used a master server and then they just ran this command called rdate, which would go to the server and say what time is it, and you just set your clock to that time. okay, without even accounting for propagation delays, which were ignored. Okay, but now you can do better than that. Okay. Any questions on this so far? Okay. So next we are going to talk about what might seem to be a slightly disjoint topic from clock synchronization, but we'll see why it is related. Okay, so we'll talk about the global positioning system, or GPS. Okay, most of you know what GPS is, I presume. You use GPS to find directions to go from one location to another. Okay. So we'll see how the GPS system works and why it is related to clock synchronization. Okay. So basically the way GPS works is you have, or here's the problem of what, here's the problem that GPS tries to solve. Suppose that you have a node. Okay. It could be a GPS receiver, it could be a computing device, it could be a phone. It doesn't matter what it is. It's a node with GPS capabilities. And what this node is trying to do is it's trying to figure out its current location. It doesn't know its location and it's trying to figure it out. Okay. So the question is, how is a node supposed to find its location? That's the problem GPS is going to solve for. And the way GPS solves this problem is it has other nodes called beacons that know their own locations. Okay? And they will transmit their locations to any other node. And so by listening to this transmission, you're supposed to triangulate or figure out your own location. So the idea is you will have some nodes in the system that know their locations. I'm going to draw another picture here, and then you'll see why that picture here makes sense. So let's say I have a node here. It knows its location XY. It knows where it is located. Okay, when you deployed it, you figured out the location and you encoded it. Okay. And this node is going to broadcast its location. Okay. So let's say wirelessly, it sends a packet saying, I am node X, this is my location. Okay. And then you broadcast it. Okay. Now there is some other node, let's call that X1, Y1. There is a GPS node here, a GPS receiver, that is trying to figure out its own location. Here we are going to only look at two-dimensional space, so that's only two coordinates, X and Y. In reality, you have to find your location in 3D space, so there will be X, Y, and Z, which we'll talk about in just a moment. Okay, so this node needs to find out. So X and Y are unknowns. X1 and Y1 is known because that's a node that knows its location. Here is a node that doesn't know where it is. It wants to find its location. Okay. So what the GPS receiver will do is it simply listen to this broadcast. Let's say it receives a broadcast message. Okay. The idea is that by listening to this broadcast and the location of a known beacon or a known location of a beacon, you have to figure out your own. So how do you do that? So let's say it takes time t for a message to go from this node to this node. Okay. So if you know that it took time t for a broadcast to be received, and the question is, what could the potential location be? Okay, so first we have to realize how to find this distance. Okay, let's say, you should know that all wireless broadcast traverse at the speed of light. The speed of light is a known entity. Okay, so the distance, if it takes time t for light or a wireless broadcast to go from this point to this point, this distance is going to be the speed of light times that t. Okay. So if you know how long it took for this message to be sort of to traverse from this point to this point, so t is known, speed of light is known, so this distance is now known. If this distance is known and that point is known, then what coordinates could that node have? Sorry? We'll come to that. How to know that time will come to that. I'm simply trying to build it up. Okay. Good question, but for now, let's assert we figured that t. Okay. So I'm simply asking, if you knew t and you knew this, what are points that are at a distance d from any given point? Sorry, what did you say?
Square root of x.
Square root of x. Okay, so I'm asking for something even more simple.
Big circle.
Okay. So all points that are at distance d from this point will be on a circle. Right? So that's the property of a circle from elementary geometry. What are all the points that are at a distance d from a point here? They're all a point that lie on a circle. They're all equidistant from that point. Okay, the circle will have a radius of d. Okay. So what this should tell you is you cannot triangulate yourself from one beacon. All you can know is I could be at any of these infinite points that lie on a circle, but I don't know which of those points you are actually at. Okay. So all that you have done is from a completely unknown location, you have figured out you are at a distance d from this beacon, and so you have narrowed down the locations to point on a circle, but you don't know which of those locations you are. Okay. But you are at least done something better than not knowing where you are at all. So now you repeat. Okay. Let's assume there's a second beacon that's also broadcasting its location. Okay. It knows its location x2, y2. Okay. So it will also do this, and so now you will basically say this distance is t prime. That's the time it took for the broadcast to be received. Okay. So then where is this node with respect to that node? It will be on another circle. And those are the two circles shown here. So that's the first beacon. That's the second beacon. Okay. So with respect to this beacon, this unknown node is on this circle. With respect to this beacon, this unknown node is on that circle. So now these two circles have to intersect, otherwise something is wrong. So you may have up to 2 points of intersection. So now what you have done is you have narrowed down from a circle because you have to lie on both circles, and these are the only 2 points that lie on both circles. You have narrowed down your position to now 2 coordinates. So rather than an infinite number of points on either of the circle, now you can be at only one of these 2 points. Okay, but you still don't know which one. Okay? So you can add more beacons and keep narrowing this down. Okay? If you have a third beacon, you can probably do it. Okay? So this is how GPS is going to work in 3D space. Okay, so you understand the point. So this has nothing to do with GPS. This is simply saying if you have beacons that know their locations, okay, and they broadcast their locations, and you can listen to these broadcast signals, and you can somehow figure out how far you are with respect to the beacon, then you will know where you are with respect to that beacon. So you can listen to multiple beacons and then try to find the intersection of all of those points, and that should tell you your own location. This is how you can, this is referred to as triangulation. And this is how GPS will also work. And now we'll come to that important point, which was how do you know T? Yeah, so there's a good question. So first, to know T, let's assume that the clocks on the beacon and this unknown node are perfectly synchronized. Okay? Let's say the clocks are perfectly synchronized. So in this case, knowing T is a trivial task, because whenever you send out a beacon message, you input your timestamp saying, I am a beacon, this is the current time, and this is my location. So you send that. When that message is received, you just see what is the time I received the message. Since the clocks are synchronized, the difference between those 2 clock values, this is the sending time, that's the receiving time of the message. The difference between those times should tell you what T is. Okay. So if clocks were perfectly synchronized, finding T is a trivial problem. You just look at the clock when the beacon packet was sent, you look at the timestamp when the beacon packet was received, the difference is going to tell you the time that message took to propagate from the beacon to the receiver. Okay, now as you can imagine, clocks are not perfectly synchronized. So there is going to be an error. What you will do is you will know the time at which the beacon sent the message. Okay? You'll also know the time at which you received the message, but the clocks are not synchronized. So the difference in those, so that let's say you send the message at time T, T1, you received it at time T2, but this clock is off, so there's going to be an error term there, delta, which you don't know because the clocks are not synchronized. Okay? So as part of the triangulation problem or the GPS triangulation problem, you also have to solve the clock synchronization problem. If you cannot synchronize the receiver, the GPS receiver with some clock, you cannot find out where you are because you cannot find an estimate of T anymore. Only if you can synchronize yourself with some other entity can you actually find an estimate of T, and then you can triangulate yourself. Okay? So to find the location of an object using GPS, you also have to synchronize the clock on that object with some other clock. So you have to solve clock synchronization as part of it, or put another way, clock synchronization will come for free when you solve the GPS problem, because you have to solve both problems at once in order to do this. Is that clear? Did I answer your question? I didn't tell you how to solve the clock synchronization problem, but I just explained how you get T. Okay, so now we will try to do this in a little more formal way. So I think I don't have a picture, but I'm going to draw one here. Okay, so we'll assume that you have beacons. Now we'll talk about actual GPS. So you'll have some beacons. Okay, in GPS, the beacons happen to be satellites that have been launched. So they are at known location. The satellite is sitting at a known location in orbiting the Earth. Okay, so it knows each satellite notes its location in three-dimensional space: x1, y1, z1, x2, y2, z2, x3, y3. There are many satellites. I'm just drawing three here. Okay. There is, let's say, this is Earth. There is a GPS receiver here that has an unknown location, x, y, z. That's unknown. All of these values are known because you put the satellite in a particular way. Furthermore, we'll assume that the satellites themselves are synchronized with an atomic clock. Okay, so the satellite is somehow synchronized with an atomic clock. It may have an atomic clock receiver and it is synchronized. Okay. So the times on these satellites are accurate. They are already synchronized. The clock on the GPS is not synchronized. Okay. We want to synchronize it as part of the process. So we'll assume these clocks are already synchronized and they know they are very well synchronized with an atomic clock. Okay. So each of these will basically send broadcast messages, which are the beacon messages that I talked about. And your GPS receiver has to receive these beacons in order to figure out its location. And here is the very simple way it's going to work. Okay, so let's say a message comes from the first satellite to the receiver. Okay, let's say this distance is d. Okay. So the message was sent from the satellite at time t. It was received by this receiver when its local clock is time t now, which is clearly not synchronized. And so then by just, since the speed of light is c here, so you'll say t now minus t plus error term delta by which your clock is off. Okay. T now plus delta is the real time. Okay. The clock says it's t now, but the real time is t now plus delta because you're off by delta, and that delta is also unknown. So t now is known, that's what your local clock is. T is known, that is what the message was sent with. This is an unknown term. Okay, so that's one unknown. Another way to compute d is the Euclidean distance between these 2 points. Okay, so this is basically what somebody had just said, the square root of x minus x square. That's the Euclidean distance between any 2 points is square root of that. Okay. Here you have three unknowns, x, y, z. Okay. x1, y1, z1 known terms. These two distances are the same. There are two different ways of computing d. Okay, so you just say this is equal to that. So that gives you one equation with four unknowns. Okay. X, y, z, and delta are unknowns. Okay. So you now have a nonlinear equation with four unknowns. Okay. Now you can repeat this with that receiver. That gives you a second equation, which is going to be the same, except that these will be x2, y2, z2. Delta is the same. So again, second nonlinear equation with the same four unknowns, and you keep repeating. Okay? Ideally, if this was a linear equation, four equations and four unknowns allows you to solve it accurately. Okay? But this is a non-linear equation. So when you solve a non-linear equation with four unknowns, you will not get a unique solution, you will get multiple solutions. The same reason why this gave you two different solutions, even though there were two unknowns, x and y. You got two different solutions. You could be at one of, you didn't get a unique one. The same thing is going to happen here. Okay, so what you do is, as you have more satellites you can listen in, the more accurate you can make your estimate. You can eliminate some of those values. Okay, if some of those values are, let's say, 500 feet above, you know you're a car, you're on the ground, you can eliminate that as a heuristic, or you can use a number of heuristics to eliminate some of this, and you'll find it. So eventually with 6 or 7 unknowns, you'll have basically you'll be able to pinpoint. Okay, but ideally, as a linear equation, you would only need 4 satellites, okay, 4 beacons to triangulate. Okay. Now keep in mind, as a part of solving XYZ, you also solved what is delta. Okay, so that tells you what your clock drift is. So you have synchronized the clock on your GPS receiver as part of finding out the location of the receiver. Okay, is that clear? Okay, so as you can imagine, you basically also could figure out the propagation delay of the message because you said that's the distance. That's the same problem you had when you were trying to synchronize the clock server. You were finding the network propagation delay. Here you basically looked at the propagation delay of a broadcast packet over air which comes at speed of light. Okay, so all of that you solve. So as part of the GPS problem, you solve the clock synchronization problem as well. So, or put another way, to find your own location, you need a receiver that's tightly synchronized. Otherwise, you will not be able to find your location because you need a very good estimate of D, which is basically that. Yes. So question is, are you assuming all the satellites are synchronous? Each satellite is synchronized with an atomic clock. Okay, so as a result of that, we'll assume they're also synchronized with respect to one another. Okay, so we'll assume they're very well synchronized with an atomic clock, hence they're relatively synchronized as well. Okay, there'll always be an error, but the error is far too small for you to worry about. So as you will, if you actually read any GPS receiver handbooks or whatever they say in the user manual, it will say it has a tolerance that you can pinpoint the location within 10 feet or 100 feet or some such thing. The reason you have that tolerance is because there will still be a small error in how the satellites are synchronized in estimates of delta and so on. So you will not find exactly a point, but you will find a small range of points. But that's good enough in most cases. Okay. Any other questions here? Okay, so we understood now how GPS works and how you solve clock synchronization as part of the GPS. So this is basically the same equations I put there, which is the delay has a clock drift and then this is the distance. So you keep solving it for each of the satellites. Okay, any questions here? Alright, so there are many other clock synchronization is a very active area for many networking researchers. It's actually used for a variety of different scenarios. So here, basically there are synchronization protocols that are used in sensor networks for small sensors that may not have a clock to synchronize themselves with the time server. So clock synchronization is wireless networks is also an active area of research for many researchers. So you use some variant of the other of either the Cristian's algorithm or the Berkeley algorithm. So you have a broadcast server that broadcasts the time. Somehow that node has to figure out what is the propagation delay. Okay? Once you find the propagation delay, you add the propagation delay to whatever the broadcast values are telling you, and you set your time to that value. That's the basic idea. Okay, and in some cases, the algorithm may be only one way. You don't actually send a request and get a reply. You periodically listen to these broadcast packets and synchronize yourself. Okay? I won't go into some of these more fancy schemes for doing clock synchronizations. They're the same basic idea. I just wanted you to know that there are many different variants. Okay? So with that, we'll talk a little bit about NTP. Okay? So NTP is now a widely used standard. Okay? If you have any computing machine, you will basically see that by default, it is actually synchronized itself with a time server. You can pick whatever time server you want. Typically, that time server will run NTP. There are many default ones. You can pick whatever you want. Okay, so UMass runs a NTP server. I think it's called ntp.umass.ed or some such thing. So you can set your machine to synchronize with that. It by default synchronizes itself with some random, not random, but some pre-configured time server. So you can actually go into your settings and you can even find out what NTP server your machine uses. So if you just go, so you will see that there is a time server. So this that time server that Apple runs is called time.apple.com. Okay, that's their NTP server. You can pick whatever you want or pick your own. You can change that one. Okay, they're all NTP servers. So your machine, most machines, Linux, Windows, Macs will actually use NTP to synchronize the local clock. Okay. So this is widely used now. So machines by default use it. to do clock synchronization. What it gives you is your clock is guaranteed to be within, I shouldn't say guaranteed. In most cases, if you run NTP, you are within 50 milliseconds of real time. That's the accuracy with which NTP runs. Okay, so you will always have an error tolerance for whatever clock synchronization you use, because you have to estimate the propagation delays and so on and so forth. Okay. So for NTP, that tolerance is typically around 50 milliseconds. Okay. Now there are two important points. So first is, it is a basic version of Cristian's algorithm, but it uses 8 measurements. Rather than asking this once, you ask it 8 times. You estimate the time T1 where you send the message, time T4 where you receive the message, and then you basically take half of that value to be the propagation and processing delay. Okay. But you do this 8 times, so you get good estimates. Okay. So that's one sort of important addition they make. The second one is, well, not the second one. The other important point is NTP can be hierarchical. Okay. You can use NTP servers that themselves synchronize with other NTP servers. Okay. So you can have a master NTP server, you can have a level 2 NTP server that synchronizes with the master. Machines can then synchronize with a level 2 server or a level 1 server, depending on what you want to do. So you can have a sequence of time servers. Only one at the root has to itself synchronize with some atomic clocks. Others will run a more fancy version of NTP. Not shouldn't say fancy, but it will run them more frequently to be better synchronized with the NTP server. And machines themselves can synchronize at whatever period they want the OS is configured to be the drift rate of the clock and so on. Okay, so it's a hierarchical algorithm. So you have a hierarchy of time servers. Okay. You can only have one, in which case it will look like a Cristian's algorithm, but you can have a hierarchy as well. Okay, but last but the most important point in NTP is if your clock is actually running fast. Okay. What NTP does is it doesn't let the clock go backwards, because that can have unintended consequences. So if you always reset your clock and set it back, that can cause a variety of problems. Okay, because now time has actually gone back on your machine. So you may have, let's say, modified a file, okay, and then you run NTP and your clock is reset 15 minutes back. So this now your clock, you're saying you did something and it's sort of in the future. So this kind of stuff can cause arbitrary problems to occur. Okay. So what NTP will do is clock can jump forward. If you're running slow, you can always jump forward. That won't cause any problem. If you jump backwards, then you will see the same event occurring twice. Let's say at 3 o'clock you timestamp the file. Clock advanced went to 3:05, okay, and then you say the clock is fast, you set it back to 2:59. Then again the time is going to run to 3 and you do something, and the old 3 and the new 3 o'clock will not make any sense because they are actually apart in time. Okay, so you can't have problems like this happen. So what NTP will do is it will slow down your clock. Okay, but it won't make it go backward. If you're running fast, it will make it tick slower. It's trying to hold it back, but it won't make it go back. Okay. That is something that none of the previous discussion actually talked about. We just assume you can reset the clock any way you want. If you're faster, you move it back. If it's slower, you move it forward. But only one of those two actually works well. The other one can cause problems. Okay. So that's an important addition that NTP makes, which we did not discuss. You don't want time to actually go backwards because that can cause trouble. Yes, question.
How do you actually make it go slower?
How do you make it go slower? So you can, that's a good question. So you can't actually hold time back. Time will do what move regardless of what you want. So what you can do is you can change, so you can just think of how you actually advance the clock. So let's say by default, if you're a quartz clock, you say every time the quartz crystal oscillates by 100 times, you will tick the clock by 1. Okay. The way you can make it go slower, you can reset the value that you want the crystal to oscillate, and then you tick that. So instead of saying wait, count until it oscillates by 100 and then tick the clock, you can say make it oscillate 101. So you basically count 101 and then you will tick the clock. Okay, that basically slows it down. You understand what I'm saying, right? So you can't actually slow it down, but what you will do is the way you will tell time with respect to whatever entity you use to tell time, you will change the parameter so it ticks slower. Okay, so what will now happen is your clock will start advancing more slowly. Real time will advance at its normal rate and they will catch up. And then you will be synchronized.
So, can the operating system actually make those changes?
Can the OS make those changes? I think you can, because there are ways by which you can. You have a real-time clock chip, and there's going to be a driver for that real-time clock chip that is simply reading from that value and telling you what time it is. So you can simply configure some parameters in the driver to say now tick slower. Okay, so that's how it will work. So what you will do is you will slow down the clock and wait for time to catch up rather than resetting that time. And once time catches up with real time, then you will let it go the way it is. Is that clear? Any other questions?
There will be a noticeable lag between the time the synchronization begins and when it ends.
I didn't follow the question. You're saying there's a noticeable lag between when synchronization begins and ends? And what does that
I
mean?
mean, because you're making the clock tick slower to get the time server and your machine to the same to the same time. So there will be a time when you start that process and you end that process.
Yeah, so the question is there will be some time it takes for your clock to catch up, but it won't be long. Okay? So one simple way for your clock to catch up is rather than set it back, you stop the clock. That you can always do. Okay? You just say time is frozen, and then when the actual time catches up, you will be resynchronized. But if you freeze time over long periods or you freeze your clock for 5 minutes, that's not a good thing. So ideally you want to slow it down. Okay, so now how frequently you slow it down? So typically if clock synchronization runs frequently enough, this is not going to be noticeable to you, because even when you drift by a millisecond or slow, you will slow it down just so much. So it will look like a slow clock and time will catch up with you. Okay? If you run it every 10 days, then you might be off by 15 minutes. That may take you a long time to catch up. But this runs frequently enough because your tolerance itself is 50 milliseconds. So every time you go off by a little bit, you will either slow the clock or something like that to catch up. Okay, so you won't actually notice all this happening in the background. You won't see the clock doesn't seem to be ticking on the machine or anything like that. Okay, it won't be noticeable. Okay, so that's all we have about physical clock synchronization. So now we are going to switch gears and talk about clock synchronization, but done in a different way, called logical clocks and clock synchronization using logical clock. Okay? So basic point you want to keep in mind here is no matter what clock synchronization algorithm you use, that algorithm is going to have some error. It can never perfectly synchronize your clock with an atomic clock. So always you have an imperfect clock. You'll never have a perfect clock on your machine, even if you use a clock synchronization. So what that says is, if you try to now look at two timestamps and reason about that timestamp, okay, because of this tolerance, you can never actually tell what happened between any two events if they are sufficiently close to one another. Okay, so put another way, if NTP has an error tolerance of 50 milliseconds, okay, and let's say you have two events that are occurred 10 milliseconds apart, possibly on two different machines, you compare them, you can't actually tell which one happened before. You can look at the clock value and say maybe the clock value indicates this happened before that event, but in reality, because your error tolerance is 50 milliseconds, you cannot really distinguish. Okay, so they could have happened in the other order because the error tolerance allows them to happen in the other order. Okay? Only when the events are actually greater than the error tolerance can you reason about them in some reasonable way. Okay? When the two events are actually sufficiently close, they're within the error tolerance of the clock synchronization algorithm, all bets are off. You can't tell. Okay? So you can make your clock synchronization more and more accurate, but this problem will not go away. So 50 milliseconds, maybe you will have a new algorithm that does 50 microseconds, but then you can have two events that are within 10 microseconds of one another. You can't tell the difference between. So this problem is never going to go away. There is no such thing as a perfect clock. Okay, actually referred to as a global clock. Global clock is a perfect clock when all machines in the system can tell you perfect time. So there is no such thing as a global clock. It's impossible to achieve because all clock synchronization algorithms we know have some error tolerance. Since there is no global clock, there will always be events that you cannot use timestamps to reason about if they're sufficiently close to one another. Okay, So for most practical purposes it works, but there will be always these race conditions where you will not know. So then the question is, can we get away from this whole notion of using physical clocks to reason about time, because they will always have some errors. So can we somehow reason about ordering? So what we really want is ordering of events. We want to be able to figure out which event has happened before which other event. And we are using the timestamp on those events to reason about it. Which file was modified before which other file. We look at the modification times of files. So we are using timestamps or actual times that have been assigned to events to reason about their ordering. Can we get away from that altogether? Okay. So can we somehow just reason about the ordering without using a physical clock and the timestamp of that physical clock to reason about it? That's really the problem we want to try to address. And that is the reason for that is clock. There is no global clock. There is not a perfect clock. Okay. So we will use this notion of a logical clock. In a logical clock, we will basically ignore what the physical time is. We do not need clock synchronization if you use logical clocks. Clocks can be out of sync. We will not care. We will use some other mechanism to reason about ordering of events. Okay. So clock synchronization does not need to be absolute. Okay. And what we want is for your processes in your distributed system to agree on the order of events rather than the timing of events. We want to reason about which one happened before which one. So we simply want to assign an ordering. That's really the problem we are trying to solve. Okay. And we are using time as a way to order events. Okay, because that's an easy way to tell which event happened before. So can we just solve that problem without worrying about the actual time of the event? That's the question. Okay. So now we will define some terms. We won't solve the problem yet. In fact, we may not even solve that today. We may have to defer that to next class. But let's see if I can give a high-level idea. So first, we will basically define this whole notion of event ordering. Okay. So you can have, so we'll just talk in a little more abstract way. We'll assume there's a distributed system. There are applications or processes running in the distributed system. And there are events, arbitrary events that occur. Okay. And we want to basically find an ordering. Okay. So you can achieve a total, so basically what we want is a total order. Given all the events, and there's a timeline, you want to put the events on this timeline, and then you can look at which one has happened before which other event. And this is a logical timeline, it's not a physical timeline. So to do this, we'll assume the following properties. We'll assume that events on a single machine can always be ordered perfectly, because they are going to use a logical clock, not a logical. They are going to use a local clock. Okay. So if you had only one machine, or event ordering is not a problem. Even if that clock is out of sync, by simply using the local timestamp, you can tell. It doesn't matter whether the clock is actually synchronized, the clock is ticking forward. That's all you need to know. So if it assigns a timestamp that's greater than the previous timestamp, clock has ticked forward, so you can find an order. Problem arises when you look at two events on two different machines, because those clocks are not synchronized. You can't simply compare the local timestamp and say something. Okay, so this you cannot do. But within a single machine, this is a non-problem. You can always have perfect ordering of events across processes on the load, because there's a reference clock. Clock ticks forward. That's the only physical property you want to do. Okay. So now what do you do? In a distributed system, there is no local clock, global clock rather, and local clocks are not synchronized, so you cannot even order events. So how can you figure out in what order certain events have occurred? So we are going to use a very physical, simple property from physics, and you will think that is too trivial once you understand it, but it's actually a very nice property. So we will assume that processes are going to send messages to one another in this distributed system. Okay, this is how systems work. You have applications, they send messages to one another. So we are going to use this notion of a message exchange to order events across processes running on different machines. So within a process on a single machine, you can always order events. Single machine clock ticks forward. So each process knows what is happening locally. You don't know what's happening globally. But you do know that messages are being exchanged. Okay, so what property of a message exchange can we use to order events across processes? So the property is actually here, which is almost trivial, is that you cannot send a message before it was received. A message has to the sending of the message always has to precede the receipt of the message. That's a fundamental property from physics. So we will basically just use that property to order events. Okay, so I'm going to draw a picture here, and then we'll see how this will actually work in an algorithmic way. Okay, so we will. So this is time. Time is on the x-axis. This is process A. This is process B. Here are some local events, and since the clock is advancing, you know this is a total ordering of events within this process. Here are some other random events on process B. Those are also ordered based on time. Okay. What we don't know is we take some random event here and a random event there, and I say which one happened before which one. We don't know because we don't know, the clocks are not synchronized. But let's say now there's a message. Draw this in red here. There's a message that goes from here to here. Okay. Process A sends a message to process B. Now, the only thing we are going to say is, although we don't know anything about all these other events, we know that this event and this event, which is the sending of the message and the receipt of the message, can be ordered globally. Okay, because a message cannot be sent before it's received. The send always has to precede the receipt. These two events are ordered. Okay. So now, just by this observation, we can now order events in these two processes. Only some subset of the event, but nevertheless, we can order events. So you know that within A, this event has occurred before that event. So those are two local events. Within this machine B, you know that event and that event can be ordered. Okay, because this is two local events within this process. You also know that the send happened before the receive. Okay. So now this allows me to order basically this event on this process and that event on that process. Because by transitive property, this event happened before that event, that happened before the send happened before the receipt, and then receipt happened before that. Okay. So now I can order events across two processes. I haven't used any clock synchronization. There are no clocks. Simply by the property that the message must be sent before it's received, I have managed to order events. In particular, I can basically whatever I have drawn on the pink line can be ordered. Okay. All events before the send here would have happened before all events after the receipt in this other process. Okay. Is that clear? Very simple idea. No clocks whatsoever. All we said is you locally basically have a local ordering of events within a process. That's not a problem. That's an order of execution of that process. Now when processes exchange messages, we can use the simple property of message exchange to order events across processes. And just use transitive property. So now you can ask a question, what about the event I have drawn here and this event? An event that happened after the send but before the receive. What can you reason about these events just looking at this picture? Or perhaps that event and some other event here. Events that happen after the send and after the receive. So, as you can imagine, you cannot really say anything about events that have happened after the send or before the receive. This is a partial ordering, not a total ordering. We want a total ordering. All that we can say is all events before the send have to precede all events after the receipt here, because the send and the receive are ordered. So anything before the send and after the receipt, so whatever I drew on this pink line have to be ordered. But whatever is not, you cannot say anything. So if you are given those two events, you say, sorry, I do not have enough information to tell you which one happened before the other one. In fact, we'll call them independent. They are independent event. There is no message exchange that has occurred for you to reason about them yet. If there are other messages exchanged, there will be further ordering you can derive. Okay, so if a message goes back, you can probably now order more events between these processes. But based on the single message exchange, that's the only thing you can say. Okay, so which is all the events before the send on process A have to be happened before all the message events after the receipt. Okay. But before the receipt and after the send, those events, all bets are off. Those we will call independent events here. So we managed to get partial ordering. It's not a perfect solution, but it's nevertheless a good solution because now it doesn't matter what the local clocks are telling you, what accuracy they have. None of that matters because you know that the send and the receipt are ordered. And that's a simple property that we will assume. Yes.
So if two systems don't actually need to send each other messages, will they send a message just to kind
Yes.
of synchronize the clock, or not the clock, but just to kind of like,
Yeah.
order?
So that's a good question. The question is, if two machines don't send any messages, should we send some messages just to order events? That's your question. So the point is, if two machines never communicate with one another, there should not be a reason for you to actually try to reason about events across them, because these are two arbitrary machines. They never communicate. Why do you want to reason about an event here and an event there if they are not related? They are unrelated machines, unrelated events. So we'll just assume that they're independent.
I
So
mean, more or less like if they haven't talked to each other in a while, like maybe not never, but
So if they have not, if you need to reason about events, the only thing you can do is message exchange just allow you to reason about them. So either they actually exchange messages as part of the application or some other process that allows you to reason about it. But by default, we'll say it's a partial ordering. So machines that don't communicate with one another probably are unrelated. And so they will have events. They will assume the events are independent. We don't know what order they occur. Okay? Only when there's a message exchange, either explicit or forced, because you want to implicitly get some event ordering, can you actually reason about it. That's what we will assume here. Okay, so it's always partial. You will never get a complete ordering, but nevertheless you will get some ordering as a result of this. Okay, so let's stop here. What we will do next time is take this idea, okay, and actually come up with a logical clock synchronization algorithm that allows you to actually stamp these events with some logical clock values and try to say something about what. Yeah, this is a picture. Okay, now we have to take this idea and convert it into an algorithm to do this. Okay, and tell us what happened before what other event. Okay, so that will defer to next class. Okay, so let's stop here today. Just a reminder, I'll send an email about this. I had originally announced a makeup class this Friday, but because the lab is due and the department is having a candidates weekend event for new students, I am going to reschedule that. No makeup class this Friday. We will have that some other time. So maybe after spring break or something like that.
Sorry for not CCing the TA and putting
Not a problem. Did you get all the answers you needed? Or?
more or less. Kind of want to talk to you about using an RMI like way of doing things and like kind of our design about that.
Okay.
I was wondering, do you have time now to talk?
Only very briefly because I'm talking to this faculty candidate who is interviewing for a professor job in 5 minutes.
Okay. Is there a better time later on today, maybe?
Let us talk maybe 11 because I am going to leave for the airport a little later today.
Oh, really? Okay.
So since the project is due, shall we go up and talk now? You have something?
I have just a quick question about the special project.
You want to ask now? Or we can walk up and you
Okay,
can
just
ask me.
very quick question.
Why don't you talk? Let's talk, and then maybe at 11, if we need to talk some more, we can talk. Yeah.
Yeah. Does it matter which supervisor we use?
It shouldn't matter. At some point, I wanted somebody to play with VMware GSX and make it work with OpenStack to see what we can do with it. If you use Zen or KVM as a starting point, that would be fine.
Okay.
Which one?
After that is just install the hypervisor, install it's OpenStack working with it, then get Chef working with the machines.
That would be a good starting point.
Okay.
Just play with all the tools, you know how to make it work. Then we can do something interesting.
Okay. And then you do the project report for that too, or is that not quite? This is not the same format as.
No, don't worry about a special project. This is deadline. So we're just starting. We'll worry about that for a later stage.
Do you have any kind of sort of soft deadlines?
We can discuss it. If you have made it progress, we can try to put because people are just getting started,
Okay.
unfortunately.
So,
So I will have some that will be slightly different from the ones of the regular class. Doesn't seem to work. so I may have to. Can you come at 11?
I can come at 11. I mean, I have an 11:15, unfortunately. But...
Yeah, I'll do that. You can always talk to Tia. We have the whole week.
Oh, where's this here?
She sits in 240. So let's go now and talk to her. She'll be there.
Yeah, you want to do that? And then,
You just do that, and if you still need questions, ask me. I can call you or something.
Yeah.
I'm going to DC for the next day and a half.
Oh, okay.
So
you would call us as opposed to doing it over email?
email is fine.
Okay.
You can always send email, but I would say for face to face, because of this thing that was scheduled today, PM may be better. Just
Okay.
talk to her. If you still have questions, email me.
Okay.
If you really need to talk, let me know.
Okay. Sure.
I'm sure that between PM and me answering mail, you can get your.
I don't think the questions are too complex.
So just talk to PM and see if you are not happy with asking.
Okay.
Hi. This is Amir. Nice to meet you.
You look very sharp.
Thank you. Well, I put it on YouTube, so
Yeah,
It's
right.
sort of
It's
public.
there forever.
so I may as well look good and not look
Yeah.
sloppy.
Well, you always look good. I was going to tell him about who he's meeting with. Don't worry about Prashant. He's a
Jerome.
softie.
Jerome is next, right? So
Yeah,
I'll tell you
Jerome's
about
next.
Jerome.
Yuri's a software engineering guy. Your whole first day are really great people. Ramesh was actually the CTO of Akamai.
I know.
Yeah. Oh, you know? Okay.
Yeah,
Yeah. He's an amazing theorist. Also looking to get strongly into security, actually. Everybody here wants to get into security.
Okay.
But nobody's
Okay.
central. Andrew McGregor's tomorrow. He's this incredible new theorist. I shouldn't tell you this, but I'm going to tell you. We sent him out for mini tenure, and people wrote back saying, "Give him tenure now." Several people wrote that.
Really?
I've never seen that before.
Oh, wow.
Insane.
Don't make him nervous.
Okay.
You have to
Mark
talk to
Liberatore
such-
actually works. He was my PhD student. He left, and he's back as a research scientist. So you'll have a lot to talk to him about. He's on the PETS program committee, for
Yeah.
instance. Yeah. Okay. RG and I talked about Dave McSparrington is in charge of our teaching. I still have 1 more minute for something.
Oh, no, take your time. I'm just, I have to actually, as it turns out, it's a little bit of a crazy day, but.
Okay. So Dave, wicked smart guy, to use a New England colloquialism. But he's in charge of the grad and undergrad, so he'll tell you a lot about teaching expectations and things like that. Dave McSparrington.
Okay.
You're gonna go lunch with him in Oregon.
Okay.
Lee is in software engineering, and Lori is our chair, of course. You should talk to her about issues. She's a software engineer. I would talk to her about salaries, your deadlines, stuff like that. Okay, and then we have this thing where we do this sort of like you would do for a dinner, but there's a group of us systems people together, and we sort of have a conversation together. Sometimes dinner or lunch or these group meetings can veer into topics related to, I don't know, just life. Where it can be more friendly, but this is just sort of a shot to have it. And then it says grad students, so that's the grad reps and whoever else wants to come. And then it doesn't say it on here, but what it doesn't say is, you're leaving right after that.
Right.
Oh, in fact, there's an update to this. This is a half hour, and the grad students start at 3.
Okay.
And then when you're done talking to them, you'll find Emery again, and he'll just talk to you about your whole visit, what you thought, and then he'll wait for you until the taxi or whatever it's called. Okay?
Sounds good.
Great.
Okay.
Well, really glad to have you here. So I'll see you at our talk at 4, and then we're going to go to dinner together too.
Yeah, sure.
Okay, have a great
Thank
day.
you so much.
Yeah, see you.
Thanks, Bharat.
Okay. Good. How are you?
So you are at UT now, right?
Yeah.
I graduated from there many years ago, actually. I see quite a few people from UT here.
There's actually many people from UT here. So what's the catch?
No catch. It just happened over a long period of time.
Okay.
So I'm going to just do something. Actually, I have to put my video on YouTube, so I'm just sort of copying it onto disk for a YouTube upload. But we can talk. So I will unfortunately not be at your talk
Okay.
because of all the weather problems in DC. Some of my DC work got moved around, and I have to leave for the airport today to
For
get
PI meetings and
yeah
okay,
things
and
like
this
that.
stuff. Okay.
Yeah, So unfortunately, I won't be there. So if you can give me the sort of minute version of it, it would help me understand, and then I can tell you a little bit about what I also do that might be of some overlap with the work that you do.
Sure, absolutely. So I work on, I'm generally a network security guy with a particular focus on privacy preserving communications.
Okay.
So
Like
what is
differential privacy or what kind of?
no privacy preserving communications on the internet. So
I see.
we
Okay,
want
got it.
we want to protect users, people's communications on the internet, right? So this
You can't trace them back to where they.
right.
sent
So it
from.
ranges from it includes anonymous communication systems, like keeping private who you're talking to and how often you talk to.
And routing like things.
Exactly. Censorship resistance. In fact, this is what I'll be talking about in my lecture today.
Okay.
Which is keeping the internet accessible and open to all people. Yeah. And then this third sub area, which I call it user-driven privacy, where the idea is protecting users' private communications on internet services, including, let's say, cloud services, cloud of storage like Dropbox, social networks, voice over IP, all of these services. So the idea is we want to protect users' private information on these internet services. But that's the kind of broader view of what I'm doing.
Will you talk about the third thing today? I have some questions and we have some work that is related to that.
Right. No, actually, I talk about the second one, censorship resistance.
Okay.
Yeah. So
maybe we can talk about the third one. I will watch your talk. It will be videotaped, like my lecture, but not put on YouTube. Only available privately. So anyway, I'm done with this. So I can shut.